For the next two videos, we're going to expand on work by solving problems where there are several force vectors acting on our object. As a recap, we defined the formula for work as W equals FD cosine theta, where theta is the angle between the force and displacement vector. We also learned that the net work is equal to the summation of all the work components. So now that we have refreshed your memory, let's take a look at this problem. A moving company has come to load your belongings in a truck. During the load, a man pushes a 200 Newton box with a constant force of 150 newtons up a 3-meter ramp. The angle the ramp makes with the ground is 36 degrees. While the man is pushing up the box, he encounters friction from the ground, where coefficient of friction is equal to 0.6. Find the work done by the friction force, normal force, and by the man's push. Find the net work in the x direction. Round final answers to 3 significant figures. Well, this question was a mouthful, so for the sake of time, I drew the free body diagram of the box since we already discussed how to draw free body diagrams on an inclined plane. So now that we can visualize what is happening, we must note that the x direction is parallel and our y direction is perpendicular to the ramp. This is going to be very important when we're solving for our net work at the end. Before we can solve for work, we need to know the force value of the man's push, the normal force, and the friction force. The reason we need to know these three values is because we're going to plug them in to our work formula so that we can find the work components. The force value from the man's push is actually given to us by the problem, and it equals 115 newtons. For the normal force, if you remember from the previous unit, we derived the formula for the normal force when we are dealing with forces at an angle. If you do not remember, I advise you to go back and rewatch that video. But what we said in that video was that the normal force on an inclined plane is equal to the gravitational force times the cosine of theta. One thing I want to point out is that this angle is totally different than this angle. Remember, this angle is talking about the angle between the force and displacement vector, while this angle reflects the angle of the incline itself. That was one thing I wanted to make clear. Anyways, back to the problem. The gravitational force is given to us in terms of the box's weight. So the normal force is equal to 200 newtons times the cosine of the angle of the inclined plane, which is 36 degrees. And this will give us roughly 161.8 newtons. Also, as a reminder, make sure calculator mode, if you're using a TI-84, is in degrees and not in radians. Lastly, to solve for a friction force, you must be familiar with the formula. The friction force is equal to the coefficient of friction times the normal force. We did not discuss a lot about this concept in Unit 3, but I'll make sure to make another video about it. So since the man is moving the box, he is going to encounter kinetic friction along his path. So using this formula, we can plug in the coefficient of kinetic friction, which is given to us by the problem, as 0.6, and plug it in to this formula. So we have the friction force is equal to 0.6 times the normal force, which we calculated above, times 161.8 newtons, which equals 97.1 newtons. If you do not get this value, make sure you're using the exact value of your normal force in your calculator. Now that we have solved for the three forces, let's solve for the work done by each of these individual forces. So like we discussed, work is equal to the force times the displacement times the cosine of theta. The work done by the man's pushing is equal to 150 newtons times the displacement, which is 3 meters, times the cosine of the angle between the force vector and the displacement vector. Well, since the force vector and the displacement vector are in the same direction, the angle is 0. So the work done by the man's pushing is equal to positive 450 joules. The work done by the normal force is equal to the force, which is 161.8 newtons, times the displacement of the object, which is also 3 meters, times the cosine of the angle between the normal force vector and the displacement vector, which is 90 degrees. And this equals 0 joules. So this goes to show that even on an inclined plane, the work done by the normal force will still equal 0. Lastly, the work done by the friction force is equal to the force of friction, which is 97.1 newtons, times displacement, which is 3 meters, times the cosine of the angle between the force of friction vector and the displacement vector. And the angle between these two vectors is 180 degrees. Since the force of friction vector is opposite of the displacement vector. So this will equal negative 291.2 joules. Now for the last part of the problem, we are asked to find the net work in the x direction. And we can see that the only forces that are acting in the x direction is the man's force pushing the box up the incline and the force of friction. So all we have to do is add these two forces together. So we will have 450 joules minus 291.2 joules. And this is going to equal 158.8 joules. Before we move on to the next problem, I made a mistake and forgot that we have to round our final answers to 3 significant figures. We can still do that now, but ideally you would want to do this as you complete each step of the problem. So let's go back and fix our mistake. The normal force is going to be rounded up to 162 newtons. The work done by friction is going to be rounded to negative 291 joules. And the net work is going to be rounded up to 159 joules. So in the future, when you're solving problems, make sure you don't make the same mistake as I did. In the next video, we're going to solve a similar problem, but this time, we're going to solve for work when the force vector is at an angle.